If we have a 20-meter wire in this case, if we have a wire indicated by the central line here, surrounded by a cylinder that's concentric with the wire, the axis of the cylinder being the same as that of the wire, then we can make a symmetry argument to claim that the electric field on the surface of the cylinder at every point except close to the ends is uniform and normal to the surface. Okay, so first of all, why is the field normal to the surface of the cylinder? Well, that happens if the field is radial from the line. That means you've got the line charge and the field at every point is pointing directly away or directly toward that line. So total field, well, let's see. If we sketch the line, assume we got positive charges uniformly distributed along the line. Then, if we want the field at this point a little ways from the line, the field, the contribution from the left will clearly be somewhat to the right, because every point here is going to lie at, well, the r vector from any point here to this point is going to be in this direction. Now, the points closest to this point here are going to tend to push away in this direction, but as we include the points further and further away, well, it turns out that we get a field that might look something like this. It might be a little more this way, a little more this way, but it's inclined to the right. The field to the right of this point will be inclined to the left. Now, there's a little more stuff to the right here than there is to the left. There's a little more of this line charge on this side than there is on this side, because this point is a little closer to this end than this end. So the contribution of whatever would be here isn't present, so that the vector we have here is going to be a little less in magnitude than the vector here, and actually a little closer to vertical. You put that together, this vector being a little longer than this one and a little further from vertical than this one, we get a total field that's inclined a little bit that way from the vertical, a little bit to the right. And when I was saying contribution from the right and left, I was thinking of people being here and their right and left. Actually, I just confused my right and my left, but you get the idea. Okay. We conclude that the field's almost but not quite vertical at this point, vertical in the plane of the board. There's more charge to the left than to the right, and that should be left and that's right. Though the charge that we have on this side that we don't have on this side is pretty far away. So the distance is pretty great, and you don't have a huge difference, meaning that this total field is going to be pretty darn close to vertical at that point. So except near the ends, the field is nearly radial. Now, why is it radial? Well, it's radial because it's perpendicular to the line by this argument, or very nearly so. So your field kind of looks like this. Now, when you get close to the end, if you're right at, point right away from the end here, right to just to this side of the end, I'm not going to say right or left because I appear to be confusing that today, but a point right here, just past the end, excuse me, all the charge is on this side of it, so all the charge is pushing this way. Okay, so the electric field will be this way, and similarly over here. And as you move from a point here to a point over here, let's say, the field gets closer and closer to being perpendicular to the wire. Here's another symmetry. If I cut this wire at the center here, assuming this is the center, then flipping the wire should make no difference in the field. So the field over here should be a mirror image of the field over here. Flipping the wire doesn't change the fact that you've got a charge distribution, in this case 4 microcoulombs per meter on a 20-meter wire. Okay? It's still the same if we do this. And it's also still the same if we rotate the wire. So looking at it from the end, we have an end view that looks like this. And rotating the wire can't make any difference in the field because you still have the same distribution. So if one of these vectors is bigger than the other, then if I rotate the field, well, then the vector over here is bigger than the other, but the field can't have changed. The conclusion then is that the field is immune, being immune to rotation, has to be uniform on any cylinder coaxial with the line. Okay, so we conclude that, first of all, almost all the flux is perpendicular to the cylinder, because you've actually got to be pretty close to the end on a small cylinder before you get any of this end effect. So from here to here, the flux is pretty much radial and perpendicular, but radial and uniform on any cylinder. Okay, so we draw this conclusion. Now that's a quick argument. You need to work through that. Just kind of an overview of the argument. The flux is 4 pi kq, where E is uniform and radial because of all the things we talked about. So the flux is then going to be just the magnitude of the uniform field of uniform magnitude on that surface multiplied by the area. That's going to be approximately the field times the area of the curved surface. The area is just circumference times length, 2 pi r times L total. In the case of the dimensions here, that comes out to be 17 square meters, the quantities given on the problem. The flux then is 4 pi k times the 4 microcoulomb total charge. I said something about 4 microcoulombs per meter, but actually this is just a 4 microcoulomb total charge. If I did it right, that comes out 4.5 times 10 to the 5th Newton meter squared per coulomb. So the field, the magnitude of the field, there's no arrow over the E, that's the magnitude, is flux divided by area. This divided, the flux divided by the area comes out, I think, 3.6 times 10 to the 4th newtons per coulomb. You're welcome to check my numbers, okay? Now we come down to this question, the radius, r, length L, charge per unit length is lambda. How much charge is there? Now we have this same wire, if you wish, and a shorter cylinder around it. And we're going to make the point that a shorter cylinder, a cylinder that is considered to be far from the ends, much further from the ends than any point on the cylinder from the wire, will give us the same result. We don't have to draw the surface over the whole cylinder. The total charge is going to be what? Length times lambda, length times charge per unit length. The total flux is then 4 pi k times the charge, which is L times lambda. The area is 2 pi r L, circumference times length. So the electric field is the flux over the area, which is 4 pi k L lambda divided by 2 pi r L. And the L divides the L, and the pi divides the pi, and we end up with 2k lambda over r. If we plug in lambda as the 4 microcoulombs divided by 20 meters, which would be 0.08 microcoulombs per meter, I believe. Now it would be 0.05 microcoulombs per meter. That'd be our lambda. K is what it is, and R is the 0.14 meters that we used previously. We come out with the same result that we did here.